Yeah, my name is Omar. I'm Daniel. Our presentation is about automorphism groups of paired crustaceans. To understand what any of those words mean, we gotta go a little bit back. So, what a graph essentially is a set of vertices and edges combined together that make like pretty shapes like this. But they can also be a lot simpler ones. But yeah, it's a collection of edges and vertices. And then the graphs we're focused on are graphs with the following properties. They're planar, simple, 3 connected, and 3 regular. And here's our example of some of those, but I'm gonna go into depth with like what these characteristics are. So to be simple, you wanna have no multi-edges or no loops in your graph. So here's an example of a multi-edge, and then here's an example of a loop, here's an example of a multi-edge. A loop essentially is an edge that connects to itself on the same vertex, and a multi-edge, wait, did I say that twice? A multi-edge connects two of the same vertices, twice, an edge that connects to vertices twice. And then to be planar, you want to make sure you can embed your graph onto a plane without any edges overlapping each other. So here's an example of what not planar is, right? Because all these edges overlap each other right here. And then to be 3 connected, you want to be able to remove 2 vertices without the whole graph like disconnecting essentially. So this is like not 3 connected, because if I remove these 2 vertices, the whole graph disconnects. So we don't want that in our graphs either. And to be 3 regular, all that means is that every vertex has 3 edges to it. So here's an example of it being 3 regular, what we want. And here's an example of being 4 regular. Same thing, just every vertex has 4 edges. I'm not concerned about that though. So once you have all these characteristics, you get what we call a crustacean, right? And what's special about these crustaceans is that we can paint them in a certain way. And when you paint them, this can also be referred to a perfect matching in graph theory. But the rule of thumb when you're painting them is that each vertex has 2 unpainted edges and 1 painted edge. So, if you take a close look, every vertex has that characteristic. So now that we have crustaceans and painted crustaceans, one of our goals during the summer was to find out all paintings of certain crustaceans with 2 to 6 painted edges. And then another one of our goals was to differentiate which ones are similar to each other and which ones are different from each other. I'll be going over like how to tell whether they're still the same, and then Omar will be going over how they're different. But how to tell that they're the same if that there exists an automorphism that maps one painted crustacean to another one. And what an automorphism is, essentially, here's the definition if you want to read it, but it's just like a transformation, right, that changes almost nothing of the graph. It looks almost identical once you perform it, but some edges and vertices might swap around with each other. So, for example, in this one, you can see how after the transformation F, I think B and E swap, essentially a reflection over this line. So again, it preserves all adjacency, but some edges might swap around sometimes. Here's a simpler automorphism of a crustacean. You can see all I did was flip it 180 degrees, and when I do that, it looks exactly the same, but some sides do swap. Now we can perform these automorphisms to painted crustaceans, and when we do that, if there exists automorphism like that maps a painted crustacean to another one, we can say that those 2 are equivalent. And then here's a less trivial way to do automorphism. You can choose any region in the crustacean to be the unbounded region, and then essentially, you like draw the line around the graph, and then we kind of like rotated it a little bit to make this line straight, and then you get this shape right here. And then over the summer, we just kept doing this multiple times to all crustaceans. It took a really long time, but our goal again was to tell which are different, which are similar to each other, and we're going to group up all the ones that are similar to each other to something that we call a equivalence class. But here's an example of what we did, right? So for this crustacean right here, we found that you could paint it this much, like 4 different ways, right? And then what we found out, or what we did for multiple crustaceans, is that the only ones that really matter are P and Q. P is completely unique. Any automorphism to that keeps it the same. But from Q, I can perform automorphisms to get, itself Q, R, and S. So we essentially did that for all painted crustaceans. And now my friend Omar is going to tell you how to tell whether they're different or not.
Thank you. So then to tell if painted automorphisms are different, we first want to go back to the normal crustacean and talk about something that are called essential edges. An example of an essential edge is this top row right here. What we're going to do with the crustacean is remove the edge and its associated vertices. So then I remove edge 1, and then I remove its associated vertices, and we end up with a graph that is not a crustacean. As Daniel mentioned earlier, this is a graph that has a multi-edge, and because that's the case, we consider it to be an essential edge. And now, notice how we have 3 essential edges highlighted. The reason why that's the case is that now we're going to be performing a technique called a 3-edge cut. So those essential edges, we're going to remove them from the graph, and we're going to end up with a disconnected and simple graph. Now, doing this technique with the 2 paintings we care about, paintings P and Q, with the blue dotted line highlighting the 3-edge cut, the number of red edges it passes differ. And because the number of red edges it passes differ, that is one way out of many to show that paintings are not equivalent. And now doing this process of showing paintings are equivalent and not equivalent, we end up with the table of painted crustaceans and their equivalence classes. Another example is this crustacean, which we consider to be K4. K just represents the number of vertices of the crustacean. So we only have 1 painting here, but there was 3 paintings in total. And from those 3 paintings, we found automorphisms that mapped every painting to one another. So all we cared about was the painting that had the most symmetry, which is why we have that one there. And then these are the 2 paintings which Daniel mentioned earlier. And then we went up to 4, 5. Here are some more of the 5 painted crustaceans. And we went up to 6. There is a lot for 6. This is the first couple. This is the next set of crustaceans and their painted crustaceans equivalence classes. And here is the last set. So then our goal, as Daniel mentioned, was to find all the total paintings and reduce the amount to look at to see by seeing which ones are equivalent and not equivalent. And the reason why is with regards to its applications. So before talking about the applications, we want to go back to automorphisms. Before, we just cared about automorphisms that transform the graph to get, or to map the graph to get itself, but we didn't care about the painted red edges. Now we do. This is an example of one of them, this painted crustacean. It's automorphism, the red edges stay the same, and what we did was a reflection down the middle. And the reason why they're important is because painted crustaceans come from something called flat fully augmented links. And this is something within topology. And here's just a quick example of how to get from a painted crustacean to a flat fully augmented link. And the reason why they're important is that every automorphism that preserves the painted edges is also a transformation of the flat FAL. This is an example. So then this painted crustacean gives us this flat fully augmented link. In the last slide, the reflection down the middle was one of the transformations that preserve the red edges. That same transformation, or the symmetry of the link, exists for the flat FAL it corresponds to. And then that was the applications of what we did with the table. And then something else we did with the table was try to relate the paintings to each other, paintings of differing red edges. So then last summer's research group, they went over a process called segment addition. This is where we had a crustacean with an example K8, and with segment addition, they went up to a new crustacean of K10. So we wanted to see if we could expand this idea onto painted crustaceans, and we did that with the process called painted segment addition. Here is an example of the same crustacean, just with a specific painting. We get a crustacean and a new unique painting to it. And the reason why, when doing this, we found that there was some limitations with it. An example is with this new crustacean. On the right, we have a painting of the crustacean, and on the left, we have 3-edge cuts. Earlier, I mentioned that a 3-edge cut consisted of essential edges. Notice how this is some of the 3-edge cuts. The essential edges that are shown on the left match the painted edges on the right. So then we found out that if every painted edge is an essential edge, we cannot get that painted crustacean through painted segment addition. And then this was all that we had time for throughout the summer. Here is some of the questions that, or some of the paths that we just did not have time to get into. So then, the first one was just, what are some other ways to show that paintings are equivalent and not equivalent? And then the second one was just, what are some other limits of segment addition? And then just to end things off, that's everything. Thank you everyone for being here and listening. Thank you to the PATS program for giving us this opportunity, and thank you to Professor Trapp for being our mentor throughout the semester.
All right, we have 5 minutes for Q&A.